Welcome to Lecture 5 on Data Communication. Today we will discuss transmission impairment and performance. This video will cover transmission impairment, its types, data rate limits defined by key theorems like Nyquist and Shannon, and network performance metrics like throughput and latency. Data communication is the exchange of data between devices through a transmission medium. It involves hardware, binary digits, and adherence to protocols. Examples include internet browsing and mobile communication. The communication system model consists of three main components: the sender, the medium, and the receiver. Factors like noise can negatively impact the signal at any stage of the channel. Transmission impairment refers to undesirable changes in a signal as it passes through a medium. This degradation means the signal received is not the same as the signal sent, leading to information loss and errors. Impairment occurs because media are not perfect. Factors include signal power loss over long distances, resistance in conductors converting energy to heat, external magnetic and electrical interference, and environmental conditions like temperature. There are three primary categories of transmission impairment: attenuation, distortion, and noise. These affect the signal's strength, shape, and purity, respectively. Attenuation is the loss of signal energy over distance, caused by the medium's resistance converting electrical energy into heat. As shown in the graph, the key result is a weaker signal with increased distance. A real-world example is the human voice getting quieter over distance. Similarly, network cables have maximum length limits, typically 100 meters for Ethernet, because signals lose amplitude in copper wires. Causes of attenuation include cable length, where longer length means more cumulative resistance, wire gauge, as thinner wires increase resistance, and medium type, where air is faster than copper and copper faster than fiber optics. Attenuation impacts communication by causing low signal-to-noise ratio, or SNR, where background noise dominates. This can lead to receiver failure, making it difficult to distinguish bits, and data loss, resulting in corrupted packets requiring retransmission. To overcome attenuation, we use devices that refresh the signal. Amplifiers boost analog signals, including any existing noise. Repeaters are used for digital signals, regenerating the bit stream back to its original quality. Distortion is the impairment where a signal loses its original shape. It primarily affects composite signals, which are made up of multiple frequency components. Distortion occurs due to propagation velocity. Since each frequency component travels at a slightly different speed, they arrive at the receiver at different times. This phase shift alters the combined signal shape. When visualizing distortion, a crisp square wave is sent. Due to the medium's frequency-dependent resistance, high-frequency components are lost or delayed. The result is a rounded or smeared wave, making digital decoding difficult for the receiver. Phase distortion means that if the phase of a frequency component shifts even slightly, the entire byte can be misinterpreted. This is typical in wired media, but less so in guided wireless systems over short distances. From the sender's view, multiple sine waves are aligned to create a clean pulse. However, at the receiver, the same sine waves are out of sync, resulting in a messy, distorted pulse. Distortion causes interpretation errors, where the receiver miscalculates bit duration. It also leads to intersymbol interference, or ISI, where one pulse overlaps the next. In the worst case, the distortion is so severe that the receiver interprets the data as garbage. Noise is defined as random, unwanted signals from external sources. It is considered the ultimate limiting factor in any data communication channel. The four main types of noise are thermal, induced, crosstalk, and impulse. Thermal noise is internal electronic agitation. Induced noise comes from external electromagnetic fields, like motors. Thermal noise, or white noise, is caused by the random thermal motion of electrons. It is unavoidable and present in all electronic devices, often referred to as background hiss. Induced noise comes from sources like electric motors and appliances. The transmission medium acts as a receiving antenna, picking up this electromagnetic interference. Crosstalk occurs when signals from one wire leak into an adjacent wire due to electromagnetic coupling. This is common in twisted pair cables, though modern cables use shielding to minimize it. Impulse noise consists of high-energy spikes of very short duration, caused by lightning strikes or power surges. This non-continuous noise is the primary cause of errors in digital data bursts and is a critical hazard. Data rate limits are the physical boundaries of speed. This concept addresses the fundamental question: How fast can we push data through a channel without introducing too many errors? The key factors that influence speed include bandwidth, where higher bandwidth means more capacity, signal levels, where more levels per bit increase the data rate, and noise level, where less noise allows for better interpretation of signal levels. Every communication channel has a theoretical upper limit on speed. If transmission attempts to exceed this limit, bits become indistinguishable from noise. We use the Nyquist and Shannon theorems to calculate this limit for noiseless and noisy channels, respectively. The Nyquist bit rate defines the theoretical limit for a noiseless channel. It focuses on the fundamental capability of the medium itself without external interference. For a noiseless channel, the maximum bit rate is determined by the formula: 2 times the bandwidth times the log base 2 of the number of signal levels. Here, B is bandwidth, and L is the number of signal levels. To increase the bit rate in a noiseless channel, we can either increase the bandwidth or increase the signal levels. For instance, with a 3000 Hz bandwidth, moving from 2 to 4 signal levels doubles the maximum bit rate from 6000 bits per second to 12,000 bits per second. The Nyquist theorem states that in a noiseless channel, we can increase the data rate indefinitely by increasing the number of signal levels, L. However, real channels are never noiseless, and increasing L makes levels harder to distinguish from noise. This brings us to the Shannon capacity, which represents the real ceiling for data rate in noisy channels. It provides the absolute maximum theoretical limit for a channel's speed. The Shannon capacity formula defines the maximum speed for a noisy channel, calculated as bandwidth times log base 2 of 1 plus the signal-to-noise ratio. SNR is the critical factor here. Shannon's insight proves that noise limits the number of signal levels a channel can reliably carry. Regardless of L, the SNR dictates the final capacity. If SNR is high, capacity is high. If SNR is 0, capacity is 0. A comparison of the limits reveals that Nyquist calculates the theoretical bit rate, or R, based on signal levels, while Shannon determines the theoretical channel capacity, or C, based on noise. Channel speed must always be less than or equal to Shannon's capacity. Next, let's explore network performance metrics, which measure how well the network is functioning in practice. Bandwidth in performance metrics refers to the potential capacity of the link, typically measured in bits per second, or BPS. For example, a gigabit Ethernet link has a bandwidth of 1 gigabit per second. This is the promised speed. Throughput is the actual measure of how fast data arrives at the destination. Due to impairments, throughput is always less than the theoretical bandwidth. Latency is the total time delay from sending to receiving data. It is the sum of 4 components: propagation time, transmission time, queuing time, and processing delay. This concludes our video on data communication limits and performance metrics. Thank you for your attention.